Welcome to this fourth lecture, and today we are going to be talking about second order coherence theory. I'll give the broader overview of what's studied in second order coherence theory, and then at least for today's lecture focus mostly on the temporal coherence. So before we go to today's lecture, let's just quickly look at as to what we did last time in lecture number 3. So here is what we did. So we mostly look at the complex analytic signal representation in last lecture. This is a way of representing a real signal in terms of complex functions. So here this is the real signal, real electric field, and this we write in terms of V and V star, where V is the if we take the Fourier decomposition of this, then the V is the positive frequency part of V real, and then V star is the negative frequency part of the V real, and of course taken together they are the signal, and this V is called the complex analytic signal corresponding to the real random variable V real RT. So this is a very useful mathematical technique used within the classical theories in order to simplify the math. And again, as I mentioned even last time, in the context of quantum theory, this almost is this is the only way to kind of do the math. There is no other way, because we don't have we don't necessarily have real wave functions in quantum mechanics, as wave functions are mostly complex. So it's a very useful technique, and we'll see how it is used in both classical and quantum context. Okay, now also since V is real, since we deal with a real electric field, then one property that actually comes out, that V star R minus omega is V R omega. So this property will keep getting back again and again. So it's a very useful property to actually remember. Then using this complex analytic signal representation, we then saw how to define intensity and other correlation functions. So first of all, the intensity is defined as the ensemble average of V star V. And this ensemble average we had already discussed in the previous lecture. The cross correlation function is which represents the correlation between fields at point R1 T1 and at point R2 T2. So this cross correlation function actually quantifies the correlation between the fields at these two space-time points, and again we take the ensemble average of this quantity V star V, and that gives us the cross correlation function. We'll again see this one in more detail today. Then of course we can also have higher order correlation functions, and this one is the fourth order correlation function, where we have the correlation between field points at R1 T1, R2 T2, R3 T3 and R4 T4. Again, as I said, in the context of classical theory we won't be discussing it, but when we talk about the quantum fields, two particle quantum fields, then we will discuss this in quite some detail. Okay, so this is what we had done last time, and now today I am actually going to focus on this cross correlation function, which is the 2-point correlation function, and which actually quantifies the correlation between fields at two different space time points, R1 T1 and R2 T2. So let's get started. All right, so in the second order coherence theory, the generic question is as to if there is a field produced, let's say by some source, and these are the two field points R1 T1 and R2 T2, then the generic question we ask is what is the correlation between these 2 points, and the way to quantify the correlation between these 2 points is by this quantity V star R1 T1 V R2 T2. Okay, so that's the very generic question. Here I'm asking this question. I've written this question that involves both R1 and T2, but one can ask only this question only in the context of let's say space. So in that case, it would be V star R1 V R2. that what is the correlation between the field points at r1 r2 at the same time. So in that case it just involves the space coordinate. We can also ask this question as to what's the field correlation at the same point but at two different times. In that case it could be V star T1 T2, or it could be that we can also ask the same question as to what happens to the correlation between the polarization here and the polarization there, and again is the same kind of correlation function that we need to construct. So it's the same generic question which we can ask in different contexts, involving just space, involving just time, involving both space and time, involving only polarization, involving space time polarization, everything. So here this is the generic form of this question. And what's the methodology that one follows in order to answer this question? So the general methodology is that whatever the points of interest, we take the fields from the 2 points. So we take the field from here, we take the field from here, okay. Then have a way of introducing some phase difference, that phi, between the two fields. So we take the fields from here, take the fields from here, have some way of introducing phase difference between the two fields, okay. After that we superpose the two fields at some other space time points. Third point, we take the field from here, we take the field from here, have some way of introducing the phase difference between them, and then combine or superpose these two fields at this point. And then once these fields are combined, then we look at the intensity at V, which is the IRT, and by looking at the intensity, one then tries to study this correlation function V star R1 T1 V R2 T2 as a function of the phase difference. So this is one knob that one changes, one looks at the intensity, and through this one tries to understand and measure this correlation function. So this is the general methodology. Again, I have done it for R1 T1, R2 T2 space time both. One can do it just for the space, just for the time, or one can even include polarization and so on. But this is the general methodology. Okay, now now I actually want to investigate this one in all the details for time, and that's what we call second order coherence theory. So the form that this question takes within second order coherence theory in time is as follows. So let's say we have a source that emits some field, okay. Now the field at some point r naught is V r naught t, that is the representation. Then we ask the question, let's say this is the field at time t, t1, and this is the field at time t2. So we can ask the question as to what is the correlation in this field at time t1 and at time t2, which are separated by t2 minus t1 equal to tau. So what we are asking is what is the correlation between the field vibrations at this time and at this time, okay. So which are separated by tau. Again, here we are not asking about space. So it's the same. This field will actually get here after time tau. So space wise it's the same location, but it's the same space but at two different times t1 and t2, and we ask as to what exactly is the correlation between the field vibrations that are separated by time tau. So that's the question we are asking, and this is the generic question within second order coherence theory and time. That's the generic question, and what I'm going to show is just one way of investigating this question, but this is just one way, one interferometer, but there can be several such interferometers. Okay, so for this what we do is we first split this field. Our aim is to pick up some field from here, pick up some field from here, which are separated by, and these 2 points are separated by some time separation tau. So in order to do that, what we do is we divide this field using a beam splitter. So half of the field goes here, half of the field goes here, and then we have a way of introducing a delay, a relative time delay between the two beams by this mirror arrangement. So if we take this arrangement up, then that kind of introduces time delay in this arm compared to this arm. So we have made 2 copies of this beam, and then we combine these 2 fields at another beam splitter. Of course, part of it goes through the other port of the beam splitter, but we are not talking about that. So we are just looking at what comes into this port. So this field goes like this, and part of it comes this way, this field goes like this, and part of it comes this way. So what we have over here at R, the detector location, is that we have a field coming from this arm and a field coming from this arm. So field coming from this arm, that is that has taken, let's say, time t2, and the field coming from this arm, that has taken, let's say, some time t1. So what we have okay, this should be the opposite. What we have coming from this arm is the V R naught t minus t2. Why is that? This is because, so here the field was V R naught t, and this field, this has taken time t2 to get here. So what we see at R right now is, or at time t, is the field at V R naught here at time t minus t2, because that's the time it actually took. So the field that was here at R naught t, that will actually get here at time t plus t2. So what we are seeing, the field here at time t, that actually is the field that was there at R naught t minus t2. Similarly, what we see here now coming from this side is, coming from this side is actually the field at R naught at time t minus t1. So the field at the detector R and t basically has component coming from RM1 and the second one, and this contribution is essentially the field that was there at R naught at time t minus t1, and this one is essentially the field at R naught at time t minus t2. So what is this field VRT? That means the field at the this detected location. So this field at this detected location we can write as V RT, and that's, this has two component. One is V coming from the first term, which is R naught. This is the field at R naught at the origin at time t minus t1, and then we have other component which is V at, again at R naught, but at a separate time, different time, and which is t minus t2. Now of course, since there is a beam splitter here, there is a beam splitter here, there may be losses or whatever. So there may be an overall constant k1 over there and a constant k2 over there. So that's the field we see at RT, which is again a superposition of fields at R naught at time t minus t1 and at time t minus t2. Okay. So now the intensity at the detector is IRT, and that is, as we had defined earlier, V star RT and VRT. Ensemble average. So that's the field and that's the intensity. Just simply just a simple formula that we have applied. V star RT, VRT. Okay. Now you want to calculate this quantity intensity in terms of by expanding this V. So let's do that. So if we expand it, then IRT is equal to, we have this first term, square of this first term, mod square, and mod square of the second term, and then the cross term. So the mod square of the first term gives me k1 mod square, and then V R naught t minus t1 star V R naught t minus t2 and then we have from the second term is the k2 mod square, and then we have v r naught t minus t2, the star of this quantity, and then v r naught t minus t2 ensemble average, and now the cross term, which is k1 star k2, and then v star r naught t minus t1 and v r naught t minus t2. Okay, and ensemble average. That's the cross term. There will be one more cross term, which will just be a complex conjugate of this one. So that's the intensity. Let's just rewrite it, and we know that okay, this is just k1 square, k1 mod square. This quantity that we have here is essentially the intensity at r naught at t minus t1. So we can write it as intensity at r naught at t minus t1. This quantity over here, this is k2 square, and this is again just the intensity at r naught at t minus t2. So that gives me sorry, no ensemble average. Let me take the okay, so k2, and then simply this is intensity at r naught at t minus t2. Okay. Now this quantity, this is the cross term, so this is just the cross correlation function, and so this we write as k1 star k2, and then this cross correlation function gamma r naught t minus t1 r naught t minus t2. So that's the cross correlation function, of course the complex conjugate. So now we see that the intensity at the detector, we have represented that in terms of the cross correlation function of the field at this point. The cross correlation is between the fields at t minus t1 and t minus t2. So the intensity at this detector is connected with the cross correlation function at the source, separated by these 2 points, t minus t1, t minus t2, and of course the intensities. So now by looking at by measuring or by studying the intensity here, the hope is that one should be able to measure this, study this, and so on. So that's the generic method of second order coherence theory, and that's how one actually studies the correlation function and does the measurement. Okay. So now before we get into, again, this is easier said than done. It is not that for any generic field this can be done. There are one can do it very effectively, efficiently for certain kind of fields. For certain other kind of fields it's very difficult to do as far as the measurements and everything is concerned. But this is the general methodology when it actually can be done. So now we get into some essential mathematical concepts that we require to handle at least those cases in which we can indeed measure the correlation function. Okay, so the first concept is the concept of stationarity, and here I am specifically mentioning stationarity in time, temporal, and this will become clear when we actually do stationarity. In stationarity, it means something doesn't, that's a traditional meaning. There's something that doesn't change with time, but we can also have something that doesn't change, with space and angle and so on, and that's where we will actually generalize this concept of stationarity. That's why I'm putting temporal here. So what is this concept of stationarity? So this says that a random process is said to be stationary when all the correlation functions are independent of the origin of time. What this means is, let's say this is the correlation function. Here I'm taking a very generic correlation function of order 2n. So we have n starred quantity and n non-starred quantity. So R1 T1, Rn Tn, Rn plus 1 Tn plus 1, and so on. Now, if the process is to be stationary, then all the correlation function has to be they have to be independent of the origin of time. So for this function to be independent of the origin of time, what we need to have is that this is equal to this. And what is this? This is just this correlation function, but just translated in time. So instead of T1, it's just T1 minus T, and Tn minus T. Instead of Tn plus 1, it's Tn plus 1 minus T, and so on. Just translated in time. So it's just shifting the origin of time, that doesn't change the correlation. If that happens, then the process is said to be stationary. Usually, experimentally, it is very, very difficult to calculate all the correlation functions of all the orders. So in most physical situations, one looks for wide sense stationarity. Now, what is wide sense stationarity? In the wide sense stationarity, one only asks for if the for the mean and two-time correlation functions to be independent of the origin of time. So as long as the mean and the two-time correlation function are independent of the origin of time, we call it stationary, or rather wide sense stationary field. Okay, so more precisely, so how do we do mean? So mean is there's a v function, let's say at r at time t, and we take this ensemble average, that's the mean. So if this is equal to, or this doesn't change, if we change the origin of time, let's say just right now we will change this by t. So if this is equal to this, then we say that the mean is independent of the origin of time, and this simply then means that this is equal to v r 0. So the mean of the function is independent of the time. So at t and at t equal to 0 is the same thing. It doesn't change. Similarly, the intensity also is independent of the time. So what does that mean? So intensity is defined as I RT, and this is defined as the ensemble average of V star RT and VRT. Now, if this has to be independent of the origin of time, then we have to have that V star R t minus t, we are just shifting it by time t, and then V R t minus t. So, and this then essentially means that this is V star R 0 V R 0, and this is essentially the intensity at R at time 0. So this says that if intensity has to be independent of the origin of time, that essentially means that intensity at time t is same as intensity at time 0. So the mean and intensity doesn't change as a function of time. So that's what it means. Now, what about the cross correlation function? What does it mean to have to be just independent of the origin of time? So the cross correlation function we have that is given as, let's say the more generic one, if we take, that is gamma R1 T1 R2 T2. This is defined as the ensemble average of V star R1, let's do T minus T1 just as in the last example, and V R T minus T2. So, that is the cross correlation function. Now, if it has to be independent of the origin of time, then we should be able to add or subtract some time argument, and then the thing should still not change. So, let us say we do T minus T1 and let me just add plus T1. So, similarly here V R T minus T2 and plus T1. So, here I have T minus T1, T minus T2. So, here I have added plus T1 in this one and as well as again plus T1 in this one. So, here we did minus T minus T, but here I am doing plus T1 plus T1. So, it should not matter at all as long as it is the same quantity being subtracted or added. Okay. Now, if this is the thing, then it means that this is basically equal to V star R 0, sorry, it is not 0, it should be T minus T1 plus T1 goes away. So, what we end up with is T, and this one is V R T minus tau, where tau is T2 minus T1. Okay. And this then we can just write as well, this we see that this does not depend on T1 and T2, this only depends on T and tau, and T is there in both. So, we can, this is essentially gamma R T and R T minus tau. Okay. So, what we have here is that the gamma that was T1 T2 and if it has to be independent of the origin of time, that it has to be equal to gamma just T minus tau. So, in fact, we can write it if we just do not write the R1 R2 notation, then we can see if we just take the time arguments, we can write gamma T1 T2, this two time argument thing, that is equal to gamma of tau. Okay. That means if it is a stationary process, that means if it is independent of the origin of time, then the cross correlation function depends on time arguments only through their difference and not in the absolute terms. Okay. So, that is the meaning of stationarity or wide sense stationarity in terms of mean intensity cross correlation function. And if we only look at the temporal effects, then it means that the cross correlation function, which is a function of two variables T1 T2, has to be dependent only on their time difference, and then that is when we call it stationary. Okay. Now, this cross correlation function gamma of tau, it has certain properties. So, let me just list those properties. The first one is that the gamma of 0, that means when there is no delay. So, when there is no delay, this gamma of tau, gamma of 0 this has to be greater than 0. Okay. This simply means that the correlation at tau equal to 0 has to be positive. I mean, if it is 0, then only way it can be 0 if that there is no field. So, that is when it can be 0. The second property that we have to have is that the gamma at some finite tau, and the mod of that has to be less than gamma of 0. That means the correlation function, the degree of correlation, the correlation function should be maximum at tau equal to 0, and as tau increases, this quantity has to be less than what it is at no delay. Of course, this can decrease and increase, but all that it says is that this cannot become more than the value at tau equal to 0. But this does not say that the gamma tau has to monotonically decrease. No, it can decrease, again increase, but it just cannot come up to the value of gamma of 0. The last property here is that the and this is actually same as we had done it for the analytic signal and the real signal being real. So, gamma of minus tau that is equal to gamma star tau. So, this we will see this property we will see keep coming back again and again, and this basically is the kind of hermiticity condition, ensures that the B, that the field that represents a physical field as opposed to some arbitrary imaginary field. So, this hermiticity condition ensures that this is the physical field that can that means that field can be realized in the lab, that field can be produced by a real source. Okay. Now, the other concept we want to look at is the spectral properties of a time domain random process. So, this is motivated by the fact that quite often it is much more convenient to study the temporal correlations of a field in the frequency basis. In time and frequency are the conjugate basis, just that sometimes it is easier to do things in time, sometimes it is easier to do things in frequency. This is same as the coordinate transform. Sometimes it is easier to do things in Cartesian, sometimes it is easier to do in spherical, cylindrical, and so on. So, this is just that. However, there is one problem, because if it is a random process, let us say VRT, if it is a random process, then its Fourier transform does not exist in the usual sense. And this is because VRT, that is a signal, is not absolutely integrable, which means that the VRT dt, this integral being less than infinity, this is not satisfied for random signals. So, what do we do? In fact, there is a formal way of handling this, and that is called the generalized function theory done by Wiener, but we are not going to go into that. But we just use the fact that even though this function is not absolutely integrable, the correlation functions are actually square integrable, and this fact is actually used to derive the spectrum and study the random process in the frequency domain. So, here we will just assume that the Fourier transform of the signal actually exists and that it can also be inverted. Again, I am kind of pointing out that this is a random process, and again because of this thing, the Fourier transform does not exist in the usual sense, but there is a sense in the there is a way in the sense of generalized function theory in which one can show that yes, there is a transform that exists, but again we do not go there. So, we just assume that the Fourier transform exists, and we will write this V as a Fourier transform, but right now we will just mean it in some symbolic sense, and we will give its physical meaning only when we calculate the correlation function and not this signal itself. So, this is the field. So, we are assuming that this field has a Fourier representation and that it can also be inverted. So, we write the field V RT as a Fourier transformation, and as we had seen, it is basically we write the frequency domain signal V tilde omega, and then the Fourier modes e to the I omega t, and then integrate it over omega from negative infinity to infinity. Oh, actually this should be, since we are taking R as well, so we have to so it should be r omega. Okay, r we are just keeping because this real signal has both space and time, but I mean what we are doing while we are doing this temporal second order coherence theory is mostly the time that we actually are concentrating on. Okay, so now this equation, this is a Fourier transform, and as I just said now that we just take this Fourier transform in the symbolic sense, and we will try to ascribe physical meaning, try to derive some physical meaning only when we calculate the correlation function. So, this Fourier transform we can also invert, and we can then write it as V r omega, and that will take 1 over 2 pi. This is for the normalization, proper normalization, minus infinity to infinity. There are different ways of doing it. Some people usually define the Fourier transform as 1 over root 2 pi, 1 over root 2 pi, but here I am doing 1 here and 1 over 2 pi here. So, this is V r t e to the plus I omega t dt. So, that is the Fourier transform of the signal and its inverse. Now, let us calculate the cross correlation function. What is cross correlation function? That is V star r1 t1 V r2 t2, the ensemble average of that. So, if this is the representation of the field, then how would the cross correlation function, how does it look like? So, we have a we have a double integral and then first one is star r1 omega 1 and then second one tilde r2 omega 2 and the plus I omega 1 t1 e to the minus I omega 2 t2 d omega 1 d omega 2, and this whole thing ensemble averaged. Now, in this entire thing, only these are the random signals, random variables. This V star r1 omega 1, V star V r2 omega 2. So, what this means that this ensemble average essentially works for this product. These are non-random functions, so they are not affected by the ensemble average. So, I think so we can actually just write it as, we can get rid of the from here, and we can write it as the ensemble average over there. Okay. So, that is the V star, that is a correlation between V star r1 t1 V r2 t2, we can write it like this. And this equation actually can be written as like this, where this is this is the cross correlation function r1 t1 r2 t2, and this quantity we are writing as w r1 omega 1 r2 omega 2. Of course, this remains the same, and this quantity is called the cross correlation cross spectral density functions. That is V star r1 omega 1 V r2 omega 2, and that is represented as w r1 omega 1 r2 omega 2, and that is called the cross spectral density function. So, just like this cross correlation function, this represents a correlation of the field at time t1 t2. Cross spectral density function, this represents a correlation in the field at frequency omega 1 and omega 2. That is that. Okay. So, now this is what we have derived. I am just rewriting it here. There is nothing new, and in fact, this can actually be inverted. This is the same thing as written from last page, and then if we invert it, there is a 1 over 2 pi whole square it becomes, because the v, the signal involved 1 over 2 pi, so that's a square now. And in fact, if we since we are studying only the temporal effect, so right now, so let's say R1 R2 equal to R, or if you just don't write the space arguments, then the above equation we can write it as just gamma T1 T2 equal to W omega 1 omega 2, this quantity, and the inverted form would look like omega W omega 1 omega 2 in terms of gamma T1 T2. And this set of equation, these two, this is called generalized Wiener-Khintchine theorem, which relates the 2-point cross correlation function to this 2-point in frequency cross spectral density function. Okay. So that's the generalized Wiener-Khintchine theorem. I'm just rewriting it here. There's nothing new. Now, for this cross correlation function, this is the correlation in time, and that represents the correlation between frequency omega and omega 2. So for this function that represents correlation between time t1 and t2, one can define the degree of temporal coherence, and the way it is defined is as follows. The degree of temporal coherence, we define it as quantity called gamma, small gamma t1 t2, and this is, we take the cross correlation function t1 t2, this just is a way of normalizing it, and then we divide it by gamma t1 and gamma t2 and take the square root. Okay, and in fact this gamma t1 is nothing but the intensity, so we can also write this as gamma t1 t2 divided by the square root of intensity at t1 and the intensity at t2. So if you take the cross correlation function and divide it by the two intensities, IT1, IT2, then that gives us the degree of temporal coherence. So this but again this quantity is actually a complex number, so we call it complex degree of temporal coherence, and the magnitude of this quantity is called the degree of temporal coherence. And of course, this degree of temporal coherence gamma T1 T2, the mod of it has to lie between 0 and 1. 0 meaning no correlation between the field points at T1 T2. 1 means perfect correlation between field points at T1 and T2. And this will see as to this function we'll study in more detail when we actually do examples of fields. Okay, now so this was the very generic case, and that's why we call it generalized Wiener-Khintchine theorem. But let's say if it's a stationary random process, if the random process is stationary, and then that we just looked at in the last couple slides back, that if it's a stationary random process, then the correlation function gamma T1 T2 is essentially gamma of tau, where tau is T2 minus T1. Now, if gamma has to have this form, that means if gamma has to have if gamma T1 T2 has to depend only on tau, then what we see that this side depends only on tau, then of course this side also has to depend only on tau. It cannot depend on T1 and T2. Now the only way this can happen is this omega W omega 1 omega 2, which is this. So the only way this can happen is if W omega 1 omega 2 has this kind of form, that is S omega delta, which is the Dirac-Delta function, delta omega 1 minus omega 2. So if and only if omega W has this form, that is S of omega 1 and delta omega 1 minus omega 2, then only this side depends only on T1 minus T2. Otherwise, for any other function form, this side will depend both on T1 and T2. But since we want this to depend only on tau, the only way it can happen is this. So the point is that for a stationary random process for which the correlation function takes this form, the cross spectral density function has to be in this form, and this S of omega is called the spectral density. It actually represents the strength of individual monochromatic component in a random field. Now, if that is the case, that means if it's a stationary random process, so if it's a stationary random process, that is a form of gamma, and again by default then the W has to take this form, and if that happens, then we need to substitute this one in here. So that's the S omega delta, there's a delta function, we can integrate it over one variable of omega 2 to get rid of the delta function, and so then what we end up with after we do the integral is the following. So what we have, at least on the left hand side, we'll get gamma of tau, and one integral will go away, so it's just a single integral minus infinity to infinity, and inside we have just S of omega. So since it's a single integral, we are not writing omega 1 or anything, it's just S of omega, and then e to the minus I omega tau d omega. So this integral for the stationary random process becomes just this. So here we have T2 minus T1, and that is giving us this tau after doing this this delta function integral, and this integral can then be inverted, and then we can see that this can be written as S of omega equal to we have again minus infinity to infinity gamma of tau e to the plus I omega tau d tau. There's a square here, that's just the 1 over 2 pi, and that's why that's because when you do the delta integral, there's a 1 2 pi involved, and that's where it actually goes away. So this is the for a stationary random process, that's the correlation, and that's the spectral density, and these two are related by a Fourier transform, and this is called the Wiener-Khintchine theorem. The other one was generalized Wiener-Khintchine theorem. This is just called the Wiener-Khintchine theorem, and in this case the degree of coherence, which was defined like this, we can see, we can write it as gamma of tau equal to capital gamma tau, and then this IT1 becomes since this is this will be independent of time for the random process, this IT1 is just like I at t equal to 0, IT2 is also at I equal to 0, I at t equal to 0, and this square root we can get rid of. So this is just intensity at 0, because for a stationary random process intensity is anyway independent of time. So the degree of coherence function in this case is gamma of tau by the intensity at t equal to 0. So that is the degree of coherence function in this case. Okay, so two more concepts. The third one is the time average, and this is a very useful concept because in realistic physical situations it is actually impossible to calculate the ensemble average, because that requires having many realizations of the physical phenomena. So in the situation in which one is left with a single realization of the physical phenomena, the quantity of interest is the time average. How do we define the time average? Let's just define it. So the time average of a quantity, the field V, is defined as, so we write V RT, again the angular bracket, but now this time we will write a T, just to distinguish it from the ensemble average, and it is defined as VRT dt integrated over some minus t by 2 to t by 2, and then we divide it by 1 over t in the limit capital T going to infinity. That is how we define the time average. Now, although ensemble averages are always equal to the expectation values, time averages become equal to the expectation value only for a particular class of random process, which is called the ergodic random process. So, only when we know that the process is ergodic, a random process is ergodic, we can actually use time average to replace ensemble average. So, for ergodic process, ensemble average can actually be replaced by time average, otherwise not. So, first we need to see what is ergodicity, what is an ergodic process, because if we know that the process is ergodic, then we have one more much nicer and much easier way of calculating the ensemble average, which is just by the time averaging. Now, so stationary random process called ergodic if it satisfies the following condition. What is that condition? Since it's stationary, the gamma will depend only on tau. So, now if this tau minus the mean of the function, mean of the random signal and the square of it, in fact we take the square, okay, and the this absolute value, if this goes to 0 in the limit tau going to infinity, then it is called an ergodic process. Although it looks a little complicated, but what it essentially means is the following, that this correlation as a function, this correlation gamma of tau, that should tend to this quantity, and that should happen sufficiently rapidly such that a long time realization, if you take the random signal for a very long time, then that long time realization can be broken up into several shorter time realizations, and each of those individual realizations has to remain much longer than the time period over which this gamma tends to be this quantity. And if that happens, then the ensemble average of these ensemble average from these different realizations, this time realization, then equals the time average over just one such realization. Then the point is that if a field is stationary, as we defined earlier, and ergodic as we are defining it here, then the ensemble average can be replaced by the time average. The ensemble average is basically equal to the time average. Okay, just one more point here. Now, in classical ENM, we define the intensity in the following manner. So, this is the real field, you take the square of it, and then this is the time averaging over a few cycles. So, in classical electromagnetism, we define the intensity like this, but we are defining the intensity using complex analytic signal in a slightly different manner. But it can actually be shown that this time average thing, this time averaging over a few cycles, this quantity is actually same as this quantity. And this I will actually put as a homework problem to actually show. But the point that I am kind of trying to make it here, that the complex analytic signal here, at least in this example, yields a definition of intensity that is equivalent to the one in classical ENM. So this definition of intensity that we had is same as what we get in the classical ENM, but this definition of intensity, we cannot have an analogous version of it in the context of quantum mechanics. But if we take this kind of definition, then this actually just translates as it is functionally even in the quantum theory. So, this is quite useful. The complex analytic signal way of doing things is quite useful, as the mathematical structure remains the same in quantum mechanics as it is in classical theories. Okay, so we will stop here today. Thank you.